Alright, and welcome back everyone. In this video we're finally gonna conclude our discussion on operators used for vector fields. Okay, this video is gonna be our conclusion to the operators for vector fields, so give yourself a pat on the back, where hopefully we're making progress. Earlier we've talked about divergence. Now, divergence and curl are actually the two main operators, the two main operations on vector fields that we should be familiar with. And a good understanding of divergence and curl and intuitive feel can really help your understanding of subjects like fluid mechanics, transport phenomena, etc. Even electricity and magnetism if you're into that. So yeah. Earlier we've talked about divergence. Yeah, we talked about divergence, right? Divergence. So we developed we tried to translate this operation, this del dot operation. We said that we translated it as the net outwards flow of a vector field, or another way to represent this, if I were to be very informal, net how much crap comes out. So if I were to be very informal and unprofessional, how much crap comes out, how much net crap, okay, now we're make it slightly more professional, how much net crap comes out of a small element, of a small volume. In 3D that's going to be volume, in 2D that's going to be a infinitesimally small area, in 1D, well, in 1D you can't really have divergence, so I'm just gonna, yes, in 3D that's just going to be a small and infinitesimally small volume dV. Okay, so yeah, now we have the calculus notation ready. All right, now our objective is to see if we can come up with a similar English translation. Can we come up with a similar English translation for curl? Now, divergence, how much net crap comes out of a small volume. All right, that's divergence. Let's see if we can do the same for curl. But before we talk about the intuition behind curl, I'm just going to show you how to compute, how you're gonna compute a curl. All right, so you're familiar with the mathematics. So let's say you guys are already familiar by now, hopefully, with the del operator. The del operator is a vector that consists of your partial derivatives and the one that I've written here is in 3D in Cartesian coordinates. So I have my del operator here, and I'm gonna apply this operation to a vector field. So let's say I have a certain velocity field, and the x component is mapped by u, the y component is mapped by uv, and the z component is mapped by w. So and in some textbooks this would be written as just v sub x, v sub y, v sub z. Exact same thing. All right, just a different set of notations. And the one that I'm going to be using is this one because it's easier to say. du dx, dv dz, dw. I mean, I don't have to say x twice, I don't have to say that twice, so I'm gonna prefer this. Okay, but yeah, that's just the and what else? Oh yeah, each of these components themselves can be functions of, at steady state they're going to be functions of position in 3D. So each of these components, u, v, and w, also depend on where you're trying to compute them. All right, what point to pick in your 3D coordinate system. All right, computation. So when I say curl, when somebody says curl of v, as in the velocity field that I have here, we don't mean a bicep curl, do we? But they're not talking about the bicep curl. They're just saying you take your operator, and then cross it. You take the cross product with the velocity field. So remember, in divergence we had a dot product, but this time we have a cross product. Now some of you might remember how to take a cross product, some of you do not, and that's perfectly okay. I'll link some resources in the description so that you can revise your understanding of the cross product. It's nothing too intimidating, okay? And so yeah, so I have my del operation. Sorry, I have my del operator, which is just going to be my collection of partial derivatives once again. And I'm just going to write that down real quick. Cross that with u, v, and w. Remember, u is velocity in x, v is velocity in y, and w is velocity in z. All right, so just to give you the final answer, I'm just going to give you the final answer. The final answer comes out to be, okay, where's my notebook? Oh, there it is. W dw dy minus dv dz, okay? And that's going to be and multiplied by the unit vector. Of course, the cross product always spits out a vector output. So, and what's up next? I have what else do I have? Dow w dow x minus, so yeah, this is just gonna, you guys can fast forward this. I'm just gonna, sorry about that, this is just gonna take me a little longer than I expected. All right, that's the j hat term. That's the j hat term plus, okay, and plus there's gonna be the finally we're gonna have dow v dow x minus dow u dow y. All right, that's what I've done here is just taken the cross product. What I've done here is just taken the cross product of these two vector fields, and I'll link in the description so that if some of you don't have, if some of you have forgotten how to take a cross product, you guys can revise that. No need to worry. Okay, so now we have a computation. Now, all right, this entire term that I have here, everything here, this is basically equal to del cross v. Okay, but what does that mean? But what the hell does that mean? Now, all right, let's take a closer look at the first partial derivative. The velocity and the spatial variable that you're changing with respect to are both perpendicular. They're both perpendicular. And that's true for all of these. That's true for all of these terms. Pick dow u dow z. U is the velocity in x direction. Z is, well, change with respect to z. They're also perpendicular. So all of these terms are measured change. All of these terms are measuring change perpendicular to flow. I hope you guys can see that. Perpendicular to flow. And if it's not clear yet, then I'm going to show you some examples next. So, okay, change perpendicular to flow. But what does that even look like? I mean, I've easier said than done. So yeah, that's where we're gonna go next. Let me just hold on 1 second. All right, let's just shift it down a little and zoom in. Okay, here I have a classic fluid mechanics example, a cuvette flow. I have graph A and I have graph B, and we're gonna inspect each of these. So if in graph A, if you move along the x direction, you'll see that your horizontal velocity is not changing as you move along the x direction. As you can see that you pick a point and move along the x direction, the velocity does not change. But what happens, okay, what happens if I move along the y-axis? Now let's see. Oh, here I have a smaller arrow. I go up. Oh boy, my arrow is bigger now. Move up again. Oh, my arrow is getting bigger. Do you guys see that? The derivative of u with respect to y is actually positive. The horizontal velocity is increasing. The horizontal velocity is increasing in the y direction. What about this one? And give this one a try, and I hope you guys will see that this one is moving in the opposite direction. So the change is going to be, the respective signs are going to be opposite. And okay, now I'm just going to grab the equation that I had here. Give me 1 second. All right, this is going to be, I can snap it, copy. All right, oops, paste it here, and I'm just going to try to shrink it down. Ooh, this is not going to be that easy. All right, easier said than done. I got it. We got this, boys. We got this, ladies and gentlemen. We got this. All right, so if I were to measure my curl for each of these fields, oops, too many blooper reels, sorry. So yeah, del cross V as given by this equation at the bottom. You'll see that all of these terms would vanish. Like there is no velocity in Z, there's no velocity in Y, there's no velocity in Z, and we're not our flow is 2D, so we get rid of this term as well. The only term left is gonna be the last term here, okay? And I'm just gonna make a statement and you guys have to confirm that for yourself. Case A has a negative, graph A has a negative curl, whereas graph B has a positive curl. And using this equation, I want you to confirm that. All right, that's going to be your assignment that I'll probably never collect. Okay, now let's move on. Oh yeah, I had another case for you guys. So imagine if you had some fluid. Imagine you had some fluid that was being it's basically wind. We're talking about wind that's blowing towards a wall, and it's gonna look something like this. Okay, and if you do a computational fluid dynamics problem, you'll realize that when you have wind incident on a wall, the resulting flow pattern looks something like this. So if I were to draw the streamlines, I have flow coming in, flow that is being rotating away, flow that is being rotating away from the wall, right? Because due to conservation of momentum, we'll talk about that. We'll talk about the dynamics later. But now you can see that there's a rotation. There's a rotation above x equals 0, and there's a rotation below x equals 0. The rotation above is counterclockwise, and the rotation below is clockwise. So the rotation above has a positive curl and the rotation below has a negative curl. And once again, I'm just giving you a visual feel. I'm not going to give you a rigorous solution here. All right, I'm just giving you a visual feel. So this right here has a positive curl, while as below x equals 0 you have a negative curl. And here I have two final examples. All right, as you can see, this one here, the rotational flow has been further exaggerated. Now flow A, in what direction is A rotating? And I hope you guys can see this is anti or counterclockwise, anti-clockwise, counterclockwise, same thing. Whereas B is clockwise, right? And therefore A is gonna have a positive curl, whereas B is gonna have a negative curl. And how am I arriving at that conclusion? I'm using the right hand rule for vectors. And yeah, I'll try to link that in the description as well. Right hand rule, vectors. Okay, so by now we have explored curl in some detail, right? And let's see if we can update our discussion. How am I gonna update this? Well, I'm just gonna say that curl is a measure of the rotational tendency. It's a measure of the rotational tendency of the fluid, of the vector field. Rotational tendency of a vector field. All right, so yeah, how much is your flow, to what degree is your flow trying to rotate? All right, that's going to be your it's going to be mapped by the curl. right, thank you very much, guys, and I hope you guys find this video helpful. All right, see you guys in the next video.